what I want to pitch to you, this is an adaptation of Judea Pearl's ladder of causation. I want to make the case to you that we can think about causation in geography through this ladder in a useful way. And so in the ladder, the way we think about it is our lowest level of causal thinking is this bottom rung seeing or associations. We might think, does the relationship between X and Y vary across location S? Most geographic research sits at the bottom rung of causation in this ladder. Where we might want to move, and where many of us are already moving, is this second ladder of intervention, asking the question of, what if we change X in location S? What happens to Y? And what if we think about questions of zoning? So we can think about what if we change the unit and scale of S? What happens to the relationship between X and Y? And then ideally, our holy grail is thinking about counterfactuals. When we're thinking about X and Y, what would happen if X had have been different in the past? And if we think about transportability, what happens to the relationship between X and Y if we move it to location S? And so this is how this is the pitch that I want to make to you today. I want to make two provocative claims which you may very well disagree with. The first is that when we think about GeoAI and GI science and the great achievements in that field, we are masters of the what of where. Synthesizing data, explaining patterns, describing patterns, and so on. We have many new technologies coming along that can really help us in better utilizing the what of where. If we want to move to the why of where question, this is where we need our human geography colleagues and those who take theory seriously and causal reasoning seriously. For our GeoAI models, we need theory, we need assumptions, we need structural causal models that we can embed in our GeoAI processes. And so potentially the best vision of causal research in geography sits at this intersection of harnessing technologies around the what of where and using causal reasoning from the best version of geography potentially focused on the why of where. I just want to flag one project that we're working on where we're trying to integrate a team. We're a team of GeoAI scientists, geographers, and cognition researchers. And we're pursuing this question of why brains age faster in some places than others. And so what we're effectively doing here is we're asking the question of, to what extent do places have causal effects on risk of Alzheimer's and related dementia outcomes? And so this, in the pitch that I'm making you today, is just one example of the types of questions that we should be aiming for as a broad discipline in collaboration and in integration. Okay. With that, I hope we have some great conversations, and please feel free to reach out if you're interested in any of this work. Thanks. Off you go, Son.
Yeah.
Jump in.
Yeah, sure. Hi, this is Song. Today, I'd like to share some of the key issues of GeoAI in the area of large language model. Actually, some of the issues I will echo Mike's keynote this morning. First is definition of GeoAI. And, together with Yuan, in general, we first of all, we emphasize the integration of GIS technology with AI, focus on the data-driven, knowledge-guided, spatially assisted, machine deep learning model development. On the other hand, in the world of agentic AI, so we can also think about, GeoAI can be considered a subject to develop those intelligent computer programs, such as agent to mimic the process of human perception, spatial reasoning, and also, knowledge discovery about geographic phenomena. So in terms of scientific issues, so Yuan and her colleagues and have a nice framework, not only about the modeling, aspects about GeoAI, but also those social, responsibilities such as transparency, ethics, accountability. So taking it further in my position paper, I want to highlight some of those issues, for example, the representation gap and then the uncertainty. So we know that the large language models are trained, in those sequence tests in the orthographic modeling way. But our geospatial world, we have various kinds of data. We have, point, polygon, 3D, etc. So this is why there is a representation gap. So luckily, we do have, for example, two approaches to address this gap. On one hand, if we want to take an analogy test, we can use the well-known test as a representation for our geometry. However, our experiment is showing that there is still a gap in uncertainty if you, telling their large language model with even different decimals of the coordinates, you actually you will see different results. And also you can using the location encoding or spatial representation learning to encode those geospatial data in the latent space. But still you will find out there is some still gap when doing those downstream tasks. So looking further, we know that we have various kind of, geospatial data. And then the recent Nature paper published last week also talking about how to just using the nest token prediction to unifying those multi-model, training for the foundation model. So the question for us is, so what would be the basic geospatial token for the geospatial data? Is a point, is a pixel, or it is a local graph, right? So if we can, also has been posed by keynote, also many other scholars in the audience, and we will focus on the local model. So here on the left, you can see that we train some local model using street view imagery about house price, in different cities. So we know that if we train the model in Boston and trying to predict the house price in Detroit and vice versa, you'll see diagonal, you'll see a totally different spatial pattern. So this is the impact of the spatial bias in training or doing the inference for the local GeoAI model. So you probably will think, okay, maybe adding more data, adding more spatial representative samples in the foundation model world might mitigate some bias degree. But on the right hand, so you will find out the gap still remains. So we focus on, for example, just still using those street view imageries, focus on to identifying location of those street view imageries using those vision language foundation model such as GPT-4V. And we found that actually, highlight some of the heat map here, they are only able to identify or only position those imagery in certain locations. So the spatial bias still exists in the foundation model world. So this is why I think there's definitely more things to do and for GeoAI researchers. So last slide. And also the importance of geo alignment and also ensure the AI system can behave based on the social norms, values, and goals. We all know that some of the bad examples about if you giving a person, and then for certain roles you will bias to certain race, ethnicity, etc. Right, and then the biasing this those major companies actually giving much worse examples. Right, we all know that some of the story from those major AI players. So in terms of geo alignment, so because of spatial heterogeneity and also spatial dependence, we need to think about what are the implications when we want the AI system to align with geographic phenomena and the spatial distribution. So this is why we thought that the geo-alignment is, if we interact with AI system, it's going to be defined as giving any all queries, like here, belongs query sets, and they should also a geographic distribution. This is a prior, and then we think that the AI system should give you the answer that should be aligned with some local or geographically appropriate distribution of the outputs. Then we think the AI system you are interacting is geo-aligned. So this is a very generic definition, but I think that this is a first step towards more spatially debiased AI system, and we have more issues like hallucination. I think because next speaker will talk about hallucination, so I skip that.
Thanks, Tom.
Yeah.
All right. Hello, everyone. My name is Xiao Huang from Emory University. And today, I know everyone is really hyped about geo foundation models. So this talk serves, let's say, just make yourself calm down a little bit about this hype. So today, I'm going to talk about geo hallucination. And I did a really interesting experiment. I give this weird hand with 6 fingers to ChatGPT 5.2 and ask how many fingers are there. And GPT told me it's 5 fingers over there. And I said, count again. So it's still 5, right? So it turns out those foundation models are not doing a counting task. It's inferencing based on a common logic, common knowledge. It is a hand, so it has to have 5 fingers. This is the model we have been relying on for a lot of tasks nowadays. So I met with Michael Batty a couple of months ago, who challenged me to write something negative about geo foundation models because he's not a huge fan of it. So I said, okay. I accept the challenge. So I wrote a solo article to his EPB titled Geo-Hallucination in Urban Analytics, What It Is and Why It Matters. We know that large language models are everywhere in our society, right? We use that to review articles, to judge policies, to simulate urban activities, to understand urban scenes and maybe facilitate urban designs. But do we really understand how those models are making the decisions? Can we really trust them? That's something we need to understand. So we did an experiment. So we used the MIT Place Pulse dataset, which is the cross-source dataset that allow people to understand or compare two different street views in terms of which one is safer, which one is wealthier, which one is more beautiful, right? And we want to know that, comparing with large language model judgment, how those judgments align with human judgments. Okay, so we just want to compare their alignment. So it turns out that for the best model we're using, GMA3 with 27 billion parameters, the alignment is only 74.2%. And for the other models we're testing, is fluctuating around 15%. Okay, so the models are not making the decisions as human. And actually, we tried different versions of the model. We tried 0 shots, we tried few shots, we tried chain of thoughts, we tried in-contextual learning, but the performance is not improving that much. Okay. So we also mapped the entire logical chains of these models using causal graphs, and we know that from these logical chains, we understand the models, the explanations provided by the model emphasize on the visual geometry most of the time. And the AI explanations encode perception shortcuts in terms of comparing to the real understanding of social spatial behaviors. It means that we really need to ground those foundation models towards the social knowledge and towards the spatial knowledge. So this is a very interesting example. So this is a very rich community with well-trained bushes. So from our perspective, from a human perspective, we know that it's a rich community with great maintenance, right? So it has to be safe. It's a safe community. But from AI's perspective, from the foundation models, the logical chance goes, people can hide behind those bushes. So when you walk by, they will jump out and attack you. So this community is very dangerous. That's AI's logic. Right? So you can see a huge alignment. This is what I mean by unreasonable perceptual shortcuts from the foundation models. Okay? And this is really dangerous. So I define geo-hallucination as the production of geospatially inaccurate fabricated information by those models we've been talking about, not rather than from the model's spatial recognition and reasoning, rather than from the inaccuracy of the source data. So this is my definition. By the way, we have a minute. Do you guys know how to make the first question work? How to make AI really count fingers in that case? Any guess? One of the strategies we use is to remove the concept of hands. You have to tell AI, this is not a hand, it's a body part from an alien species. You have to remove the concept of fingers. You have to say, please count the joints that are sticking out. Then the foundation model is doing the counting task instead of inferencing from the common logic. Okay. Well, with that, thank you very much.
Hello, everyone. So today I wanted to discuss one of our very ambitious projects which we recently completed or are in progress at Harvard, and that is using AI for studying human flourishing. So human flourishing has been a branch that has been studied for centuries, but when we were designing this project, we started thinking of, hey, how AI can help us study human flourishing in a different and new way. And the objective of this work is that we wanted to come up with 46 spatio-temporal indicators for human flourishing. And traditionally, human flourishing has been using surveys to come up with these indicators. However, we thought that in the age of Gen AI, how we can use social media data, where billions of people are expressing their lived experiences online. So can AI help us do that? And so do that. So we used 2.2 billion geotag tweets, and we applied large language models at scale on these tweets. So firstly, we use several LLMs were used to create an initial data set. Then we brought the humans in the loop to clean the training data set. And then we fine-tuned 2 open source models. And then we ran the fine-tuned LLMs at scale on these billions of tools to see if we can get some pattern for flourishing. One of the biggest challenges in this work was the computing infrastructure. So this work uses 1+ million GPU hours, and we want to do this globally, and we have still only processed 10% of the data for US, and we have used 1+ million GPU hours on Harvard supercomputer, and we ran out of GPU hours. Then we said, how do we do this just to complete for US? Then we reached out to NSF and said, we want to do this ambitious work, would you help us? And they gave us 24,000 more GPU hours to complete the work for US. And we want to scale it globally, so you can imagine the challenge here. How do you even scale this process globally? We are seeing some interesting results emerging from this study on these 48 indicators. One of the indicators I want to highlight here, which is showing interesting pattern, is life satisfaction, how there is a rural-urban divide and how people are expressing their thoughts on life satisfaction on social media across US. And this is a preliminary result, but these are the kind of patterns we are trying to study from the results here. So this work was part of NSF's iGuide Spatial AI Challenge. And so this has produced high granularity global indicators for human flourishing for United States. And we have made our AI Python notebooks all replicable on the iGuide platform. The AI models and data source are all open source now for anybody who is studying similar topic to use our models and try to work on top of that. And we are coming out with publications on the dataset and use cases of what these findings are showing us initially. Yeah, thank you.
Hi everyone, my name is Levente Juhász. I just started a new position at the University of Florida, and so I'm returning to my roots in geomatics. And really, the talk that I brought today deals with a very old problem of trying to represent something that's not flat. What? So the talk deals with trying to represent the Earth, which is curved onto a flat surface. And I argue that this is often overlooked even in GeoAI research. So this example on this slide is about Earth Foundation specifically and how they use a very high resolution approach basically built on the UTM coordinate systems, which is a system of coordinate systems. This is how it's derived from the Earth. Basically, they just project it into that cylinder. And what you see, those green lines, actually, the only lines where the scale is true, and everything else in between and outside is sort of distorted. So I did a calculation, and I used the 10 meter by 10 meter cells, which also used by Alpha Earth, along the central meridian, Daytona Beach, Florida, and it turns out that the surface area is actually over 100 square meters, as you would expect. In Tallahassee, which is around the zone edge of that UTM zone, the surface area is below 100 square meters. So there's a seemingly not meaningful discrepancy of 0.23% there. But if we scale up and we use larger pixels, that equals to 23 square meters, which is the size of a garden shed or a small room. And over the area of 1 square kilometer, it actually adds up to over 2,000 square meters. So if we are thinking about applications in carbon credits, then this becomes meaningful. And it's all because a pixel is not constant. It represents varying geographic reality. Our models, I think, waste parameters on trying to learn how to unwarp this Earth instead of focusing on the true geographic processes. Another issue that I'm seeing is that the world doesn't have edges. If you look at the figure above, Fiji and Samoa, they are less than 1,000 kilometers away. It looks perfectly fine if the map is centered on the Pacific. But if you look at the other map that's centered on the central meridian in Greenwich, then they migrate to the two sides of the Earth. So basically, you need to jump over a topological cliff. So again, we are forcing our models to learn these wraparound techniques. We need to apply clever tricks to solve a problem that simply doesn't exist on the globe. So here's my proposed solution. We should I think, try to move towards discrete global grids that are designed by the technology industry or scientific purposes, and they have a lot of benefits, I argue. For example, they can ensure metric stationarity if we use equal area solutions. They ensure topological continuity, so there are no cliffs. They are hierarchical, so we can use them in different geographic scales. They also provide spatial temporal persistence. So we could use this as a native operating system for geometrically rigorous GeoAI. So I laid out the research agenda in my position paper. Basically, I think we need to focus on this equal area framework just to ensure this metric stationarity and translational equivalence. I think it's very important that we design rigorous benchmarks so that we understand the foundational properties of these grid systems, and we can also evaluate trade-offs, whether it's worth using them or not. The more challenging part is moving toward a data supply chain that actually supports these spherical data structures. So moving away from flat geotiffs, flat sensors, and so on and so forth. And there's also a lot of issues when we think about the computational hardware. All of those are designed to work with flat matrices, basically. But I think looking into this with a critical mindset, just trying to evaluate if this is a direction that's worth pursuing for, is worthy of our thought. So if you want to read more about it, then here's my position paper. And this is going to be a very exciting period for me because I'm establishing this new lab. So this is going to be one of the main areas that I plan on focusing on. I'm also a PhD students. If you're interested, check out my website. Thank you very much.
Okay, thank you very much. My name is Yuan. I came from Virginia Tech, and I'm happy to talk about my recent work. And then largely want to focus on switch gears about how we can integrate this AI into GIS education and the lessons that I learned from teaching on new courses in the previous few years. So my work is about the human mobility and environmental health. Largely, my work is focusing on the urban planning issues. But I want to bridge the gap between the geography, GI science, and urban planning. How we can utilize this AI-powered geospatial data science methods to solve urban planning problems. So recently, in my lab, Smart Cities for Good, I have worked on these opportunities and challenges of this how when we try to integrate AI into urban planning, place-based problem solving. So for example, the opportunities is previously we used like street view images and deep learning based computer vision method to understand what is going, like walkability, safety, etc. But you are all smart people, so you all know how to use deep learning. But in the policy context, urban policy makers or people in the city officials, they do not always have the high, technical, specialties or even the computing power. So that's why I think that perhaps, this large language model or conversational AI can be the useful tool to understand, so that they can implement the AI to understand the built environment. And another thing is when we are all known about the dashboard, and the dashboard online interactive map is one of the widely used deliverable for the GIS work. But I also learned when we try to implement the dashboard in the real world with the policymakers and citizens, not all people are capable of navigating the dashboard. So there are some people are having difficulties to zoom in, zoom out of the dashboard. So that's why in our lab, we try to build a dashboard that is coupled with a large language model, so that if people say, "Oh, show me all the CVS locations nearby me," and then the AI can do the back-end analysis of the creating code or whatever SQL code generator, and then show the results in the front end. But what I like to more emphasize is about these challenges, what I call as uneven geography of generative AI's capabilities, known as geographic biases of ChatGPT. So when I ask, this map shows when I ask ChatGPT, what are the environmental justice issues of like Montgomery County, Virginia, and I ask that kind of question for 3,000 counties. And don't get me wrong, this is not the election result map. So the red color indicates the counties that do not get a location-specific answer from ChatGPT. The blue color indicates the places where it gets a location-specific answer from ChatGPT. So there is some kind of systematic geographic biases that the ChatGPT provides more location-specific answer for the high-density urban area compared to the low-density rural area. And that particularly, the challenge is very important to me because when the local planning agents, they try to utilize this AI for their solving their own problem, if they do not aware of these kind of geographic biases in ChatGPT or large language model, they assume that the AI can solve their location-specific problem. But indeed, there are some kind of geographic biases of AI capabilities, so they need to be aware of this. So at the teaching side, I try to advocate this kind of, our students need to understand not only this AI application, but also the challenges of the AI. So you've perhaps heard about this AI literacy, which is not only understand and use and evaluate, but also at the same time ethically utilize of the AI in the problem solving. So at Virginia Tech, we have developed these new courses about the generative AI application in social science, and we have seen several interesting things that have not been possible in the previous days. One example is a local planning document chatbot. So let's say 10 years ago, if I want my students who do not have the computer science background to create a chatbot, then I think that would not possible for the one semester. But these days, by using the ChatGPT or custom GPT ability, nowadays anyone who have a creative idea about how they want to apply AI to solve their own problem, they can do so many interesting thing work. So I think this is certain the opportunities for work. But at the same time, we also need to think about the limitations and ethical uses. So in the interest of time, I will stop here. Thank you.
I'm Kumar Navlur with a company called Spatial. Full transparency, I used Gemini to create this slide. So what I want to do was take a different tactic. In commercial industry, we focus on, lack of a better word, show me the money. That's where we focus on. So that means we're looking at customers, what are their missions. And my background, I was with Digital Globe, Maxar, Vantor for 20 years. And a lot of the products like the Global Mosaic is the one I created, the 3D. We also did fun stuff like non-Earth imaging. So I'm trying to take research and trying to see how can I solve customer problems while we make money as a company. So in national security, the way we talk about mission areas, there are 3 of them. We need to have early indicators or warnings of what is going on globally from a national security perspective. The other one is you're looking at broad areas. We typically think global, and sometimes very large countries, we're trying to identify a specific signature of interest. So broad area search is something we look for. And then the last one, which is now becoming relevant, is object custody. We want to basically track a given object. If you're talking something like Golden Dome project, we want to track missiles, where people are going to launch the missiles from. But we also think about other considerations like we need to deliver this thing very, very quickly. The latency aspect is very important. And when we talk about GIScientists, a lot of you're talking about identifying objects, doing land use, land cover. We actually see applications of GeoAI from tipping and queuing. The problems we want to solve are multi-modal, multi-sensors in multiple domains, space, air, land, terrestrial, and sea. So we actually see GeoAI playing an important role in orchestration of multiple modalities based on where things are happening. So we have been playing around in my previous companies for the last 8 years of applying AI. We didn't call it GeoAI. The first thing I believe is, as an industry, we don't pay enough attention to information accuracy. I think the limitation is you train with 3,000 samples and use maybe 50% to train and 50% to validate. For us, the phenomenology of just multispectral data, there are issues with data a lot of people don't talk about, which translate to the accuracy of the information you can get. So people talk about having insufficient labels. That is something I think we can absolutely tackle with different methodologies. And then the third one I talk about is lack of data reduction. The example I give is a human cognition is brilliant. If I looked at this entire room, my brain removes it. So if I put a LiDAR, I'll get like 1 billion points. But if I look around in milliseconds, I can distill to a few specific things I observe in the room. I'm not going to store 1 billion points in my brain. So we need to start thinking about how do we reduce the data for a given mission, obviously. And then the last two ones is QA/QC. I still think we should be doing extensive QA/QC because if I have a warfighter making a decision based on the information I'm giving, it needs to be trustworthy. And then the last one is the phenomenology, which Rahul was talking about. There is a reason why you have shortwave infrared bands. The machines don't know that, so we got to train them. So the last one quickly I'll go through is the value chain, how we think about it. You have descriptive. That's where most of our industry is taking an image and trying to describe what's there. And we are not good at it yet, I think. The next one is diagnostic. This is where, okay, now I found a pattern. We use the term patterns of life. Why is it happening? And then we want to go to predictive and prescriptive. This is the holy grail. When I talk about multi-model orchestration in multi-domains, we cannot have human in the loop. So we want to push GeoAI all the way to prescriptive, but we have to take steps in this particular value chain. So from my aspect, I know Dr. Goodchild, I still think we need to start with these AI algorithms to match human accuracy as well as speed. The example is I was demoing a detection of trucks in front of Army. There are 8 40-foot trucks, and the AI came up with only 7 instead of 8. So my position is let's match the human cognition and the accuracy, the speed and the accuracy. And then I think that for us, again, going back to the industry, we know that there is a lot of potential for GeoAI to solve real problems. So let's think about solving at speeds much faster than human cognition, which is what Mike's point was, but keeping in mind that accuracy is very important as well. Thank you.
Okay, hello everyone. My name is Isaac Rand, and I'm here to talk about work trying to automatically digitize the historical censuses of housing block statistics from 1940 to 1970 with my colleagues at the Center for the Restoration of Economic Data at the Federal Reserve Bank of Philadelphia. Because we all work at the Fed, I have to disclaim these views are my own and do not necessarily reflect those of the Federal Reserve Bank of Philadelphia or the system. Okay, so what are we trying to do? Basically, we have all of the census data about housing from 1940 to 1970, the housing stock itself, as well as the people who lived there. And it all exists in tables like this, just in books and libraries, which makes it very inaccessible for researchers who don't want to spend all their time digitizing the data. It also comes with these maps. The only way to link these tables to these maps is to digitize the maps and get, all of this information out of there. This is the only way also to have housing data this granular for this time period. This is the only place it exists. Okay. We are trying to publish the data for 16 cities, as well as all of our training and validation data that we use. We got a lot of hand-annotated data to do some of this work. And we're going to publish all that code and the methods so that you can use and reuse our data, but also, if you're interested in cities other than these 16, should make it easier to get the job done. Okay, I'm just going to talk about trying to georeference these maps today because there's not much time. So the way you would traditionally georeference a map is you would find 3 specific places on your map, and those same 3 places in some kind of, Google Maps, OpenStreetMap, whatever, and use those linked points to create a transformation. AI, the computer vision literature has different approaches to this problem. They call it image registration. And there's 2 kind of threads of the image registration literature that we're going to use. The first is called feature matching. It's very similar to traditional georeferencing. It's just automating the process of finding the same points in a map image and on some kind of georeferenced map. The second is coherent point drift, which is an algorithm that works very differently from traditional georeferencing. The first step is to find all of the features in both images, and then you're going to apply some kind of transformation which maximizes the likelihood that all of the features in image 1 come from the same distribution as all of the features in image 2. And here's a handy GIF of that running. Hopefully it helps to visualize the situation. Basically, the way that we use it is we take our census map image, and we can very reliably find the outline of the census map image that's easy for computers to do. and then we can find the NHGIS tracts that correspond, which come with their own georeference, because NHGIS has helpfully already done that work. And then we run the coherent point drift algorithm to line up these two outlines, and then we can use this alignment to create a georeference for this map. That works really well when the outlines map closely to each other, but sometimes the census made very different cartographic choices than NHGIS made, and you get a failed georeference using this method. Yeah, so that's when we turn back to feature matching. This is unfortunately very hard for a computer to do on its own. These images are not very information rich. They're mostly lines. This is already a simplified version of a census map on the left and the NHGIS tracks on the right. By default, you get a lot of bad links from image 1 to image 2. And you can see in these 3 examples, if you choose bad links, you get a bad georeference. So also, we've simplified this problem. On the left is a map in its full complexity. On the right is the NHGIS tracts. We trained a convolutional neural network to segment out the tract boundaries. There's still a long way to go from here, but this is the start. Then we used the magsac++ algorithm, which is an extension on ransac, if you've ever used that. The basic step of how this works is it's selecting some of the candidate links from image 1 to image 2 that it's made sure are coherent, so you're not like getting one link from image 1 into 2 totally separate places in image 2. So you're getting some kind of random subset of your links that are internally consistent, using those to just try to align image 1 and image 2, and then measuring how well you're doing just based on the cross correlation between the images, and then repeating that a lot. If you do that, 3,000 times, it really doesn't take that long, and you get one good georeference out a lot of the time. So that lets you go from these 2 images, which are pretty different, into one aligned image, which lets you put things into georeference space. This also works in our example from Baltimore before, where there's only alignment in a subset of the image, because it allows you to see where you're doing the best in your subset, as opposed to coherent point drift, which needs you to do well over the whole image. These are some results for how well we're doing. On about 1,000 sample tracks, we have an F1 score of about 0.92 on average. If this means nothing to you, over 0.8 tends to be like quite a good georeference. And we have still, though, these outliers below 0.8, where the census has just made too many artistic decisions. It was 1940, they had a lot to deal with. Yeah, thank you for your time.
Hello, everyone. Today my topic is cyber GeoAI for the new area of spatial decision support. So every day we face hard decisions. So before AI became popular, the decision support system mainly relied on databases, mathematical models, and user interface design. But today, the growing speed and volume of geospatial big data is driving us to develop a new generation of spatial decision support systems by integrating a cyber infrastructure-powered GeoAI and the human in the loop. But however, they have faced so many challenges. So I will skip the GeoAI part because you have talked a lot on that. But from the cyber infrastructure and the computing power point of view, so the CI must manage a massive amount of multi-source, multi-dimensional, and multi-scale geospatial big data, and same time supporting the interoperable spatial temporal and high-performance computing paradigms. And same time, they also have to balance the cost and sustainability. So even though we have those big machines, but scaling the computing power, but same time the lower the delay, latency, and also errors remain challenge. And from the human part, I especially want to emphasize on the cognitive overload when the users interpret the GeoAI outcomes, and also how to understand uncertainty and perform reasoning across spatial scale, and same time bridge the gap between the human mental model and GeoAI output is challenging. So now I'm going to introduce a piece of my work that related to cyber GeoAI. So several times I got stuck in College Station in Austin when there's a game day. So my navigator just tell me that, okay, you have a road closure ahead, but you are in the best route. So this motivated me to develop this reinforcement learning-based routing algorithm to help us to find the optimal route to avoid those closures. So the blue points represent the flooded area that we want to avoid, and the red line represent the best route. So I will skip the technical part. It's a long paper published by IGGS, but as a result shows that our model outperformed the traditional Dijkstra algorithms and can better, help people stay safe during those events. But we are, running the simulation on thousands of street network segments. So this poses a computing intensive issue. So therefore, another innovation of this paper is on designing the cyber infrastructure framework to scale up the computing efficiency. So another work recently, we just launched the NetCDF Faster, which funded by NSF Career Projects. So I'm not sure how many of you are working with NetCDF data. So it's really difficult to visualize. It's multidimensional, and you either have to download all the data into your desktop, or you have to query all the variables at the same time. So we have trained a massive of NetCDF data to predict the best strategy to visualize that. So based on the shape of the NetCDF files, we're gonna predict if we should visualize that in sequential or in multi-thread in parallel. And here is a video shows our user interface. So you can just drag the data or provide a URL, and we enable users to select the variables. And we compared our model with the existing tools. So for example, when the data size grow up to over 1 gigabytes, and our models perform better, faster than the existing tools. For example, the NetCDF4. But those two applications is without human interact, right? And for the first application, well, we scale up, we can run it faster, but I'm still not sure if we can provide real-time, routing recommendations. For the second one, we are turning data to knowledge, but however, how much the user should trust our visualization results. So next topic is the human in the loop. So recent news, we are hired by robots. Okay, within a few days, we have 80,000 people get hired by the robot to do the physical work. Okay, so who is the boss for such decision support? So are we controlled by the machines, or or we should be the decision maker? So my question is, what defines a good decision? Is it human satisfaction or the model accuracy? Okay, and what factors actually prevent you to using the decision support tools generated by AI? For example, the routing. And also, how do we mitigate the cognitive bias versus data and model bias, and who is responsible? So last, I want to show the one example of human in the loop that this is funded by NSF Convergence Accelerator. Okay, yeah, okay. I will skip this. Yeah, save the days. Okay.
Okay, morning everyone. During my stay at Harvard, we communicate with the people from the ecology, public management, politics, financials, and so on. And they always ask the question: is what the geo can do, what the geographical analysis can do. So I summarized their comment and put my opinions on GeoAI theories and techniques from maybe the outer communication of GIS, and actually, I have a issue. We have a dynamic document. Anyway, so 400 years ago, the Copernicus proposed the heliocentric system, and they changed our humanity understanding of the world totally. And so about the mainstream, the AI, especially spatial intelligence, which is very popular right now, they actually were similar to the geocentric system, which they developed based on the individual centric. So this limits their capacity. Limits their able of addressing like global climate change and sustainable development and so on. So Geo offers the AI the opportunity that we can put the AI, the individual-centric AI into the position that to be one member of the world, that studies the world, study world entirely. So this is why why AI is Geo, because it provides the different window to help us to understand our work. And about the geo definition, the scope of the geo. Is it the geospatial, emphasize the location-based application, or the geography, which is like the geography of digital twins proposed by Michael. So most of the activity and phenomena in the world are inherently location independent. We all agree with that. But the question is that most of the location information are not directly observable. Like how to measure visitors, like how to understand the location. People will say that I think it's a flight time, driving time, right? So in that case, we find that the space and the time are always fused together to describe the distance and the location. So we have defined the definition is the spatial temporal reality, which means that we define GeoAI should combine the space and time together. And so I think, just in my opinion, I think the GeoAI scope is AI plus spatial temporal reality. Of course, the spatial means world-centric, not the individual-centric. Okay, and then next, sorry. So thinking about the spatial temporal reality, we should reconsider about two core components of the GIS. The first is dimension, another one is scale. About the dimension, it's the dimension framework of the spatial temporality, which is different from the GIS, right? So the four dimension include four dimension that might be inadequate. And for example, the seventh dimension, is covered by this. It's the initial condition, which means that if we change the initial condition, the spatial temporal world will totally change, and we will understand how the initial condition changed the world. And actually, our navigation system works similar to this. We change the starting time and the start point and the departure time. Like we change the initial condition, right? But the navigation can always give us the best solution. This works like say seventh dimension. But the navigation maps is like the chessboard, which is in a limited world, not the open world. For GeoAI, how can we address the multiple dimensional analysis based in open world? It's still a question. That's why it's about the scale. First, the spatial temporal scale. We always will say spatial resolution or temporal resolution separately, right? Maybe in the future we should say spatial temporal resolution, which will require that we should develop a unified spatial temporal framework so that the change in any single spatial dimension or temporal dimension will have influence on other dimensions. Moreover, next one is about the visual scale and the map scale. Why? Because we know that why we develop AI, because we want to serve for human beings, right? So the mainstream of AI is human-centered. So what that means, the model simulates what human visual perception. However, this result from our ongoing research, we find that if we increase or decrease the scale, the difference between visual perception and the map generalization will increasingly bigger. So that means what it means the mainstream AI cannot fit in for GeoAI part and the application.
Sure,
So the last one is about some vision, in my opinion. The first one from the big data to deep data, because the data quality is more. Oh, so data quality is more theoretical right now, right? We don't care how much data we have. We just focus on how much qualified data we have. Another one is the things we have mentioned that the future GeoAI need to address multidimensional, multi-scale, so multiple representation should be required in the future. And the last one is about the spatial autocorrelation and the spatial heterogeneity. What that mean? Well, the mainstream AI just focus the majority data space, right? Oh, sorry. Oh, sorry. Maybe I can use 10 minutes to okay. So mainstream just focus on the majority pattern, right? But for GeoAI, the majority pattern of the spatial autocorrelation and the minority exception of the spatial heterogeneity are equally critical. So in theory, that means we should focus on the majority pattern and the long tail phenomena. And in technique, that means we should develop the integrated learning framework that both involves the statistic learning and some like rule-based or inference-based learning. Okay, this is all my presentation. Thank you very much.
Hi everyone, Diju from University of Minnesota. So I'll cut straight to the point as I feel bad standing here between us and the food, if you haven't noticed there. So let's talk about spatial network structures in GeoAI. Hopefully echo some of our discussion before regarding scientific discovery and we say the process laws in geography. So we're all talking about spatial temporal systems that are involving dynamics over there. So usually what we see are organized as consecutive snapshots of distribution data. Usually also quite spatial panel data, right? Integrated as those cross-sectional attributes on locations as well as their time series dynamics. So in multiple domains, socioeconomics, environment, that across different scales. So the shared priori that we believe GeoAI can work somehow, either we have some sort of structure, spatial structure that can be observed or measured, such as distance, structure, such as the spatial weighting, such as mobility flows that we can get. Or we have some sort of good knowledge on how we can model the process or the evolution mechanism, like gravity model, like radiation model, different kind of understanding of how the process is working on those structures. So those kind of assumptions actually determining our tasks in GeoAI when we have relatively incomplete data set. We want to rely on a strong model priori to make prediction. So if the data we believe they're good enough, we hope we can rely on them. They can review us something that's meaningful, and we treat that as explanation of the system. So here, what I want to pitch is like when we look at the panel or system that is evolving as such things, the information in between in some sort of an awkward situation where we really don't know the structure themselves, which themselves are predictable. And we also don't have any perfect laws that could explain them either. So just look at something like these structures in between the panel snapshots, like the red flows there. So what are those? Are we treating them as something as priori, or treating them as some explicit structure that can be modeled and understand? So an example here is you can get maps from time to time indicating the change of population sort of things. But what's in between? Where do people come from? Where do they go to, right? So in our recent work, we integrate this panel perspective with graph neural network and explicit modeling of evolutionary process within this panel setting. And we can regenerate, the process in between the panel snapshots as flows, right? For example, we do it at Christmas in Twin Cities, where it's cold and everyone mobility is different. We have done that for the pandemic shift in the US and some domestic travel mobility flows in China and before. So the other perspective, I'm glad we mentioned about the Felix Envy earlier. like, do they have geography envy, right? We're looking at a different system like that is more, complex or kind of stochastic, heterogeneous, and context dependent. We have seen scientific discoveries across domains using LLM to try to find out some perfect explanation for each kind of deterministic system. But we know that in geography, it's hard to find such, explaining and the laws in terms of like governing differential equations. So in one of our work recently, we tried to say whether we can somehow rank and evaluate different potential governing equations by just proposing them and fitting them and simulate based on that. So what we did is to try to say combining with the neural agent-based model and with the LLM-based agents that can generate hypotheses, like different candidates of the equations, and we try to see whether they can reproduce the observed dynamics as we often see in the systems. So we find out that indeed we can find many different ways to at least rank them and to see which one is closer to maybe our understanding of the complex spatial temporal system. So so for today's workshop, I just want to say it's more like a conceptual gap that GeoAI model structures and the process on those structures. And definitely it needs more collaboration between us and the network science. We want to incorporate explicitly those complexity idea like emergence, like scaling, like hierarchical structures, organizations with our current explicit spatial, explicit design AI. And that's all. I think I have several sessions next month at AAG where we can continue the topic as well. So thank you for your time and please.